Okay, so in today's video, I'm going to do a quick one, and the problem in this video I'm going to be doing is this, and the problem is find all points or the set, it's called the set, cap S, such that this equation is true. So you can approach this problem and it's not naive, but if you just finish with this one approach, you won't have the full solution. Just like many problems with square roots and other things like that with functions that aren't like I guess normal-ish, whatever that means. You can't really expect your solution to be the answer, so sometimes you need to check. And let's dive right in. So naively, if you were just to say, what are all the points that do this? Well, I want an equation, but I don't want the equation with the roots anymore, because I don't understand how roots work. So what would you do? You would rearrange this and square it, rearrange it and then square it to get rid of the roots, and that gives you this equation. You get 0 is equal to 1 plus x squared minus 2 x, let's do it in order, y plus x y. And let's call this equal f of x. It's an implicit function, okay? So, and it's equal to 0. Let's split it. So, this equation here, let's call the set this. And instead of s, let's call it t. T is equal to all points x, y, such that f of x, y is equal to 0. And you'll see, just because this equation comes from this equation, you don't get like I guess one-to-one correspondence of solution of this equation to the actual equation we started with. So points in here don't correspond to all the points in here. You actually get extra points in here. Okay? And how can you check that? Well, if you say, let's find a point from here that exists from this equation, independently of this equation, and then since we know it came from that equation, we can check the values of x and y that satisfy it, that are in t but not in s. So here we go. So let's do f of 2y. Actually, let's do f of 1y. So what do you get? You get this whole thing, plug in 1 for x, you get 1 plus y squared plus 1 plus 2, y plus 1 plus 1 times y, 2y plus 1 is this thing right here, -2, you get 2 plus y squared minus 2 times 2 is 4y minus 2. 2's go away. So you're left with, since this is implicit, you get y squared minus 4y. So y minus 4 is equal to 0. So you get y is equal to 0 or 4 when 4 x equals 1. So we plug that back in to here, or we check let's check if these 2 points, 1, 0 and 1, 4 are in S. So that's the same thing as, let's check a point in T and see if it's in S. Is that the case? That is not the case, but let's see if it works for both of them, or one of them. So what you get, so for 1 and 0, is that a solution to this, or is it in S? You get 1 plus 0 is equal to 1. That is correct. And what about 1, 4? You get 1 plus square root of 4 is 2. Is that equal to 1? No, it is not. And you'll see, so we got a solution here. So some points in T are in S, but not all points, apparently. So we will call this an extraneous point. Okay. So that's just to see what we got going on. So we have points that do work, some points that don't work. So just because a point is in here, it doesn't imply, let's call the point T bar in T. If T is in T, if T bar is in T bar just means any point. I'll put T bar. If T is in this does not imply T is in S. Okay. But now, with that in mind, how do we go about using T and getting S? So we want to say if, and then we need to add something that does imply it is in S. It does imply T will be in S. So we need to add this some restriction here. So where we get that some condition, like some truth statement on X and Y such that we get T to be in S. So starting from our equation, we should know X and Y have to be greater than 0 because it's a square root. And each point X and Y, or each like function underneath the root, if this is since they're both positive, if this is 1, then the other one will be, oh, you're kidding, the noisiest day. Okay. So that's it. I'm just trying to explain. You can't have any X value you want. If it's going to be a solution, X and Y have to be a certain in a certain region in the plane, or certain points. So the restrictions you get are basically this. So you get since we know let me rewrite it. So you get, if you rearrange this equation, we know 1 minus root y is equal to root x, which should be greater than equal to 0. And the same for y. And that must be true for all x. And then we also get root x plus root y should be greater than 0. We don't want to say this is less than 1, because if you have this here, it'll mess with, you won't get points that correspond to the equation. Because when you square things, you get positives and negatives when you rearrange and square it twice. So with all that in mind, you want to say all the points gamma is equal to the set of points in the plane such that these restrictions or regions are true. So they all happen at the same time too. So you get must be greater than 0. And 1 minus root x must be greater than 0. And square root of x square root of y must be greater than 0. So this basically gives you all the points that if there were going to be a solution to this equation, they better be in this region, because if they're not going to be real points to the problem. And we can use that because this will give us all the solution points and extraneous points. So all you have to do is say this S, which is all points that correspond to the solution, is basically it's equal to the intersection of all possible points intersecting this set here. So that is the same as saying this. So all the points that satisfy this equation are all the points in this set T, which is the equation, but it's all the points in the equation that are in this region. But this region is the region that is all possible points that could be a solution. So when you intersect those two, you basically just get the equation. If you intersect T with gamma, you basically just get the equation of this, all points for this equation, which is the curve. And for example, I can draw this to make more sense of what's going on. So if I was to draw two graphs, this is going to be my solution, and this is going to be T. And then I'll draw gamma on this one too. But T is this, so you get something like this. I use the computer to plot what this is, because something like this. Right? And S is now going to be, it intersects there. And S is going to be now all points of T that are in gamma, but gamma is this point right here. So it includes this point, and it includes that point, but it doesn't include that point. So gamma is all this points here. So if you intersect this region with that curve, you just get the curve here. And this is Y, this is X. So that's what I'm trying to show you. And that's basically how you could solve this problem using a naive approach. And then you can check if it has extraneous parts. It doesn't always have to, but it could. And you'll see if you don't even have to check for extraneous parts if you use something like gamma for other situations, because you'll know right away. All you have to do is just graph this curve, or only take points in this set that intersect this set. And like I said, this set is all possible points to this solution, and this is the solution that could include extraneous points because of the math way I chose to solve the problem. And that's about it.